for joining the next session of embedded software testing Unit 2 series. So we are almost in the end of this second unit. With a couple of sessions, we'll try to wrap it up, and we are more focusing on the embedded software testing, the white box testing aspects and the techniques. We will study about the white box testing techniques in more details, and in continuation of the earlier sessions. Today we will study about the branch condition testing, branch condition combination testing, if possible modified condition testing, and LC, SAJ, and NCDC. Okay. So before that, we'll just touch base on the previous session where we had gone through a table of structural coverage analysis or structural coverage types. Basically, this is what is used for structural coverage analysis. Structural coverage analysis, or SCA, is very important analysis method that they use it for industries like aerospace, where the analysis need to be provided to the manufacturers. That is like aerospace industries, manufacturers such as Boeing, Airbus, Bombardier, etc. Okay. And we started the white box testing technique with the statement testing, where we cover the statements that are in the code, and we also learned about software instrumentation, which does the intrusive hooks in terms of printf or the marks which are required within the code, so that the coverage will be traced. It's like a tracing mechanism. It's called software instrumentation. Since the code base is huge, so we cannot afford to have it manually. So there are a number of tools that are used for software instrumentation, like VectorCast, LDRA, RTRT, etc. With the help of that instrumentation, we run the unit testing statement coverage, and the coverage will give in terms of the percentage. If the percentage is not 100%, we'll do a manual analysis of the gaps, and the gaps could be in terms of decisions also. So in that case, what we do, branch and decision coverage will take care, where the coverage is done with the help of total number of executions divided by total number of decisions multiplied by 2, because 2 times it has to be the decision box need to be analyzed. Why? Because there are 2 outcomes of the decision box, that is the diamond box. It could be true or it could be false. And in continuation of the white box testing, we have gone through the data flow testing, where the variables of the data objects are analyzed in terms of the flow, and every data that are used or the objects that are used will need to be analyzed and tested. Here the data object types could be DKU, used could be it's used in a calculation or used in a predicate. So an object is defined when it is appearing in the data declaration or assigned any value, or it has been opened, a file has been opened. That is also called as an object. And if the memory using a variable is allocated, be dynamically or using constants or pre-allocation mechanisms. So this data object types are used for data flow testing, where we will segregate different types of data in different columns, such as definition, CUs, PUs. CUs is for calculation purpose. You can see X, Y, W, and Z in this example code is used as a CUs or calculation use, whereas PUs or the predicate use is Z and Y. You can see if as a bracket within that Z is less than Y is being used, so it itself is a predicate value directly within the bracket. So that is why it is called a PUs. All this data will be observed and analyzed in terms of data flow testing. It should be tested against the intended functionality or the specification of the system under test. So if there are gaps between the paths in the statements and the branch or the decision, the data flow will augment it in terms of strategies that can happen. So each of these lines of code having the data objects will be analyzed and with using different values. For example, x and y as per specification can take value between 0 to 10. We know that how we can provide the inputs from 0 to 10 with the help of equivalence class and boundary value analysis. Also, we need to consider the if condition below so that it is satisfied. It could take the path within the if, or it could take the path within the else. So all these gaps will be analyzed with the help of data flow testing. And next is the branch condition testing, which we will study today. So, okay, what is branch condition testing? Branch condition testing uses such model of the source code which finds out decisions and the individual Boolean operands. We know Boolean operands such as less than, greater than, less than, equal to, greater than, equal to, etc. So the decisions coming out of that are tested with the help of branch condition testing. A decision is a feasible statement which can transfer control to another statement depending upon the logic of the decision statement. That means decision is having a logic, having the Boolean operands, and as a result of that, the control can be transferred to different statements or a single statement depending on the logic that is being applied within the decision statement. And a decision condition is a Boolean expression which is estimated to determine the result of a decision. So decision basically is a condition, right? So it will have the Boolean expression in terms of greater than, less than, greater than, equal to, less than, equal to, or equal to, etc. So that will decide basically the result of the decision whether to go into one control or one set of statements, or it should take another set of statements. So basically these decisions are used in loops and selections. So loops, you know, it could be a while one, sorry, not while one, while loop, or for loops, or do while. Likewise, we have based on the language constructs, we have different loops. Similarly, selections in terms of cases, we know that. So these decisions are implied within this type of statements. We will see in more detail how branch condition testing is taken care. Okay, so in terms of branch condition testing, test case design aspects, how we need to have a test case design taken care. Okay, so before that, okay, so 100% condition coverage means that test data here, the coverage is also same way how we are going to do it, but 100% coverage here means that the data will ensure that every condition that is executed at least once during the testing condition coverage, that will include also the branch condition. So don't get confused with the branch of decision conditions. Here the conditional coverage in terms of the Boolean operands and the expressions part of the decisions will be tested. And in terms of designing the branch condition testing, test cases should be designed to exercise individual Boolean operand values within decision conditions. For every test case, these should be clarified before we do the design. We should have an input to the component that is part of the decision condition. For each decision estimated by the test case, identification of the Boolean operand to be exercised by the test case and its value. Expected result of the test case. So these three should be clear for the tester before he designs. So all the Boolean operands within the decision condition will have to be exercised. Operand values such as you can see an expression. Okay, let us start with a for loop only. It will be easy. For I equal to 0 to I less than 50, I plus plus and A less than B and do these things. Statement, etc. It could be multiple statements as well as a function block also would be called depending on the nature of the program. So here we have a for loop. This block will be executed how many times? 0 to less than 50 means 50 times it will be executed, where the index is I. So obviously the index will have a incrementer, or the incrementer is already there here. Based on the index, certain conditions are used. And you can see on the right hand side, along with this, it is very important to have this right hand side expression also to be satisfied or evaluated before the block is getting executed. So we know that statements, individual statements, we have statement coverage, and we know that there is a block. If A less than B, we are going to do it, and if true, this will be done. If false, this will not be executed. And now, since we have A less than B as a condition, branch condition, we need to evaluate all the aspects of A as well as B in order to test the Boolean operands. So the Boolean operands, it could be logical expressions such as or and etc. So basically the tester needs to understand what are the inputs to this block that needs to be taken care. For each decision estimated by the test case, identification of the Boolean operand to be exercised by the test case. That means what are the actions that that block is going to do for each of these Boolean operand expression in terms of inputs will be exercised, and also the value that it carries out in terms of the execution, and of course what is expected out of each conditions while it is getting executed. So that is also very important to understand. Okay, so that is about branch condition testing, and next one we have is slight modification in the branch condition combination testing. Here what we do, branch condition combination testing uses such model of the source code which recognizes decisions and the individual Boolean operands within the decision conditions. That means there could be decisions within the operand itself, Boolean operand itself. So that also will be exercised. So whereas in case of branch condition alone, what we do, we take care of the decisions and the individual Boolean operands. That's all. Here we take care of decisions and the individual Boolean operands within the decision conditions. So we have decisions. The decisions also will have a lot of Boolean operations or expressions or operands. What are the decisions that also will be exercised. This will be a rigorous thing basically. So that's why it's called as a branch condition combination testing. A decision is feasible statement which can transmit control to another statement. We know that it depends on the logic of the decision statement. That means how the logic is going to be derived. Based on that, decision is feasible. Decision is called as a feasible statement. A decision condition is a Boolean expression which is estimated to define the result of a decision. It means it's a condition basically, Boolean expression condition which is estimated to define the result of a decision. That means the Boolean expression will drive the values in such a way that the decision outcome will be known. Normal decisions are found in loops and selections. Same as here, we have a combination of that Boolean operands within the decision conditions are tested with the help of this. So each of these Boolean operands need to be tested for the variables that it is taking care. Okay. So test case design, how we are going to do for branch condition combination is as per below. Test cases should be designed to exercise combinations of Boolean operand values within decision conditions. For every test case, these should be clarified. The inputs to the component for every decision estimated by the test case identification of the combination of Boolean operands and their values, the expected result of the test case. So it's similar to the branch condition testing, but in addition, we have a combination of the Boolean operands within the decisions, all that need to be exercised. So that is the purpose of branch condition combination. Okay. The next one is about modified condition testing. So what does modified condition testing does? Okay. Modified condition decision testing uses such model of the source code which recognize decisions, outcomes, and the individual Boolean operands within the decision conditions. Here, additionally, we have outcomes also is very important. That means the output. So what sort of outputs the spec or the function that is expected. So based on the need of that, we are going to test it. How we are going to test it is with the help of all the decisions. That means decisions, individual Boolean operands within the decision conditions, and the outcomes of the result. That is also a deciding factor for modified condition testing. So we are going to have all these possible combinations in terms of modified condition testing. Addition is feasible statement which can transmit control to another statement. It depends on the logic of the decision statement. Again, the logic is very important here. Based on how and what are the values that we are going to drive for the logic, it is going to decide the output, decision output, as well as the Boolean operand within the decision conditions. So a decision condition is a Boolean expression which is estimated to define the result of a decision. Normal decisions are found in loops and selections again. So at the end of the loop, we expect some result, and the result we want as per the specification, and that result we want to achieve can be done with the help of such values which can be driven within the Boolean expression part of the decision conditions. That is how modified condition testing is taken care. Maybe we will touch base modified condition with decision coverage in detail with respect to DO100V process which is followed in the aerospace industry. Test case design aspects. Test cases should be designed to show that Boolean operands within a decision condition may be independently influence the result of the decision. That means you need to understand here. Suppose variable A and B are used to derive C. C is suppose a result. So modified condition is such that independency need to be verified. That means because of A, I am going to get the result in C, and because of B, and keeping A as constant, we are going to get the C as well. So we have two paths already. So like this, we'll have multiple conditions and Boolean expressions having the number of variables and the logic. But in all the cases, we need to measure the independency. It's very important. Independency need to be verified. So that is what the modified condition is going to be helpful. Suppose A is having some value, like some value say 0 and sorry 1, let's say, and B is equal to 0. So what will happen? A and B will again become 0, which could result in something for C, some result 1, let's say. Similarly, here we have proven that when B has become 0, C, the result of the operation, will have an impact on the output. Similarly, when A is 0, B is any value 1, 2, 3, whatever it is, but the impact is due to A because A ANDed with any of the value within the B will result in a known value. It could be result 1 or result 2 depending on whatever the expression it has. So A and B will drive independently. One will keep it as a constant, like B as said, so we will keep once 1, next time 2, next time 3. Sorry, we will keep A as constant. Next time we will verify or vary the B in terms of 1, 2, 3, etc. So the independency for B is being verified. So that is how we are going to have it. So ultimate aim is to see that the independence is achieved because of one path or one inputs. The decision condition is going to vary. So that is what it means. Test cases should be designed to show that Boolean operands within a decision condition may independently influence the result of the decision. That means the whatever I have put here is nothing but the Boolean expression having a Boolean operand as AND. So we are going to verify the operands for its independency. For every test case, this should be clarified. Same like we need to have an input. What are the inputs that is going to drive? For each decision estimated by the test case in the identification of the combination of Boolean operands, their values and the result of the decision. The expected result of the test case that also need to be understood before we do the modified condition testing. So that is about modified condition testing. The next one is linear code sequence and jump. This generally we follow not with this name but indirectly through MCDC condition testing, modified condition testing. We will add it, but certain specific industries or applications they prefer to have this. So this is a software analysis method basically used to identify structural units in the code and the unit and the test. Its primary use is with dynamic software analysis to help answer the question how much testing is enough. That means basically it will have an analysis of how much units tested in terms of dynamic software behavior or analysis. For dynamic software analysis is used to measure the quality and efficacy of software test data, where the quantification is performed in terms of structural units of the code and the test. That means based on the structural unit and its behavior or the functionality, the dynamic software analysis is used. So it is used to measure the quality and efficacy of the software test data. When used to quantify the structural units exercised by a given set of test data, dynamic analysis is also referred to as a coverage analysis. So when we are done with the dynamic analysis, we will also come up with the coverage analysis. So that is how this is done. Basically, to drive how much of the testing based on the test data uh, is needed, is what is being derived for the linear code sequence and CSSG testing. It's basically an LCSSG is a software code path fragment consisting of a sequence of code. That means a linear code sequence followed by a control flow jump and consists of the uh, so three items basically: the start of the linear sequence of executable segments, end of the sequence, and the target line to which the control flow is transferred at the end of linear sequence. Suppose we have function, one, two. I'm just mentioning with numbers like n is there. This many number of function blocks or executable segments are there in the function. So what do we do with the LCSAJ? Basically, how much I need to test for this block is what it is going to tell. That is, it's basically a code path fragment. Like I may test 1, I may test 2, I may test some 5 randomly, 10, 20, and maybe n. So like this, consisting of sequence of code is called linear code sequence. Linear code sequence, and jumping to the different linear code, it is called jump, uh, control flow jump basically. So what do we do? So we have a code path fragment consisting of a sequence of code, a linear code sequence, followed by a control flow jump. So we start with this, and then we have a control flow jump, and uh, basically this jump could be achieved with the following three types. That is start, then end. We know that we need to have end for the function block, and the target line. It means with the help of this target line, how we have jumped to the end basically. That means the target line to which control flow is transferred at the end of the linear sequence. So with the help of this will be used actually. This is basically used where we have numerous functionalities having similar expected outputs and similar sort of inputs, where we have huge number of functions. So there it is useful. So that is how they use it, the LCSSJ method. Okay. So in continuation of this, basically LCSSJ method will have the TER. It is called as test effectiveness ratio. So what is test effectiveness ratio? Is the number of statements executed by total number of executed statements, number of control flow branches executed by total number of control flow branches. We have a number of LCSG executed by total number of LCS. But altogether, we can have a TER, that is effectiveness ratio. That means how much of the code we have sequenced and jumped in terms of testing. So accordingly, we will have this sort of testing. So coverage also will take care of this. Coverage analysis metrics are used to gauge how much testing has been achieved. The most basic metric is the proportion of statements executed. Test effectiveness ratio 1, TER1, it is called as number of statements executed by total number of executable statements. Higher level coverage metrics can also be generated in particular the next level of TR2, like control flow branches. It is similar to whatever addition or the branches that we have seen before, divided by total number of control flow branches, how much is there. So whether we are able to test it, whether we are able to feed all the values. So this TR2 will give basically with the help of the sequences, whatever we have. Done. So TR3 is number of LCS executed, total number of LCSs. So these matrices satisfy a pure hierarchy whereby when TR3 is 100% has been achieved, it follows that TR2 should be 100% and TR1 should be 100%. So aim is to have TR3 as 100% so that the number of LCSJs are executed divided by total number of LCS is become 100%. So this is very traditionally old method. So both the TR1 and 2 matrices were used in 70s, and the third dates from the later 70s. The requirement for achieving the TR1 100% was the level originally selected for D1 It used to be called as TERs when they defined D1 B, where TR1, TR1, TR2, TR3, like these levels of testing they used to mention based on the safety and criticality of the embedded software. They will have a definitions of the embedded software levels. Later they have added MCDC, Modified Condition Decision Coverage, that we will study in the next slides. So it was added in 1992. Higher levels of TR3 100% has been mandated for many other projects, including aerospace, telephony, and banking. So where there is a mandate that TR3 should be 100%. It means this linear code sequence jump is 100% mandatory. One practical problem of using TR3 is that many LCSs can never be executed due to the conflicting conditions they may contain. That means we know that we have different jumps within the sequence, that is start of the linear sequence of executable statements, then the end of the linear sequence, and the target line to which control flow is transferred at the end of the linear sequence. So this basically these three units may not be executed all the time. So it is subjective, but it is mandatory. Okay. So here you see an example of a C code, and for white box testing of LCSAG, this is an example from Wikipedia. I just use it here. We have a C code having a library included here. This is library. We have definitions of macros such as maximum columns, maximum row, maximum count, iterations as 750. Then we have the main. Here we are initializing a count equal to 0, an array totals of 26 and a value, and local variable equal to 0. Then we set the memory with totals with the help of a size of that integer. Then we initialize count 0. Then what it does is while the count is less than iterations, that means 150 times, this block will be executed. Value will be absolute of some random number, modulus, maximum columns. Then totals array will be assigned with 1 and incremented. If the total of that particular value is greater than maximum count, it will assign the maximum count. Then the count will get incremented so that up to 750 times this will be executed. Else this will not be assigned. So with the help of this example, so there is a LCSJ triples, it is called. As I said, start line, finish line, jump line. Okay, so there are 8 LCSJs numbers have been identified. And start line is 10 for the first 3. Then we have the start line as 17 for the next 3, and 7th one is 25, and 8th one is 28. So based on this for loops, there are LCSJ numbers for that, and total number of LCAs are identified as 8. In the first one, we'll see start line is 10 they have used, then finish line is 17. That means, suppose say 10th is a while after this they have used, 17th is the 28th line. Suppose it is the last floor bracket. So within this, whatever is going to happen, they consider as one LCSAJ. Similarly, we have 10 and 21. And finish line is 17, jump to line is 28. That means 10 and 17. So, so this is a 10, let's say, the initialization. And we have 17, 11, 12, 13, 14, 15, 16, 17. Yeah, this is the one. And the jump to line is 28. 18, 19, 20, last one. So likewise, we are going to have start line, finish line, and jump to line. So they draw a tables for this. Okay, so that is about LCSAJ. It's a quick understanding where they use the TER, test effectiveness ratio. With the help of LCSAJs, they use the sequences, the linear sequence of executable when it starts and when it ends, and the target line to which the control flow is getting transferred finally. So that is how they are going to test it. And you can see some of the table talks about start and line the same. You see which is same here, 28 is same, and so that is the last one, return 0, it is the same, and jump to line, the last but one. Similarly, we have 17, jump to line is 28, the last line it will come from if, sorry, yes. So that is how these three aspects will be tested in the LCSAJ type of white box testing. Okay, the last one being I have added the purposefully. This is because they use this type of testing in aerospace. So very important to understand this. DO 178P testing. It is a defense standards they use. Where the different levels of safety is being defined based on the criticality and the safety level of the particular embedded software and the system. So for that type of system, the D178B mandates MCDC. It is called Modified Condition Decision Coverage Testing. So let's quickly see what it is. So MCDC, Modified Condition Decision Coverage Testing. It is more used or applicable to space or aerospace with D178B process to satisfy one of the key objectives of D178B. Also called as a truth table approach, where logical expressions are being tested. So where we have maximum logical expressions, we use a truth table. So what is a truth table? We will study that in the next slide. And there is an example snapshot of D173. How it is. I will just have a look into this. So basically the MCDC criteria enhances the condition decision coverage. We know we have seen condition coverage, decision coverage, and condition combination decision coverage. This criteria it will enhance basically by requiring that each condition be shown to independently affect the outcome of the decision. Same as the modified condition testing with the combinations. It is similar to that, but with the stringent process they follow it. The independence requirement ensures that the effect of each condition is tested relative to other conditions. However, achieving MCDC requires more thoughtful selection of the test cases. We need to have a truth table sort of approach. But if you have a 3 variables, we'll end up with 15 type of combinations. We don't need to execute all of them. So that is why it is very important to select a good approach and select such inputs. And suppose in general, if n inputs are there, minimum of n plus 1 test cases for a decision with those n inputs will need to be there. For example, A or B is there, then we'll have test cases. For example, MCDC, what we have independency, as I said, again I'll repeat, A or B. Suppose this is there, then we will have some statements executed. So A can have true, A can have false, B also can have true, C also can have false. So what are the tests that we can do it to show the independency? So the combinations could be TF, FT, and FF, so that the independency is done. We know that TT is not required because it doesn't affect the independency, and we have already tested when the A is considered as input true, and A or B will result in this true only. So to achieve the independency, we need to have the test combinations TF, FT, and FF. This will provide the MCDC. You can add a true also. Is subjective again, depending on that. Okay, here you can see the decision MCDC testing what they used. So basically, this is example snapshot of D1's energy, the different processes and sections that it has. It draws a life cycle. D1's energy software life cycle is called. This diagram is from one of the NASA document. You can see the reference here. And we have this many blocks. We have a planning. It is spoken in the section 4. This D1's energy process has a different sections. Against each sections there is a checklist, and each section will identify different aspects of the MCDC coverage and the testing process. So we have planning in section 4. We have integral process, which is nothing but validation verification. Section 6, configuration management. Section 7, quality assurance. 8, certification validation. 9. Though this will be part of the planning that needs to be addressing. Similarly, the planning also will take care of these blocks, which is dotted here. The planning will specify about development aspects. So as part of the development, we have requirements. Section 5.1, design, which is section 5.2, coding. It's all part of the section 5. So 1, 2, 3 sections are about definitions and other things. Section 4 onwards, the D1 and NB has to be strictly followed for the embedded software development. If it is a D1 and NB compliant, examples like space and aerospace industries. So there are avionics subsystems. Those subsystems need to implement based on the software level that D1 and NB mandates. So requirements, design, coding, integration. So these 4 sections are part of the development process that needs to be pointed out or supported with the help of planning, which is in section 4. Similarly, the very important part is the integral process, it is called out, which has 4 sections, which will identify the verification process, the configuration management process, quality assurance, certification validation. So Once we have this addressed, that aspects of the embedded system is called as D1 compliant. Okay. Further on the MCDC, the MCDC criteria enhances the condition decision coverage criteria by requiring that each condition be shown to independently affect the outcome of the decision. Same as whatever we have studied in modified condition combination testing. Here with more stringent D1 aspects will be addressed. The independence requirement ensures that the effect of each condition is tested related to the other conditions. That means we have several combinations. So those combinations, because once you have the code executed and a piece of code which is responsible for some outcome will definitely need to be tested and traced. So the rest of the other piece of the code will have to be constant. So the independency of this specific block will need to be ensured. How we are going to do is with the help of independence testing with the condition and the decision coverage that we have. However, achieving MCDC requires a more thoughtful selection of the test cases, as we will be discussed further in chapter 3, that is there in the D1 standard B. You can have a look with the following link below, which talks in detail about MCDC. It is not scope of this year of embedded software testing, because we are talking about in general all these aspects. If further, if you are interested, maybe you can go through in detail about MCDC for aerospace, how they have addressed. So in general, a minimum of n plus 1 test cases for a decision with n inputs. So example we have one ARB. So we have true false, false true, and false false. This will provide the modified condition decision coverage. For decisions with a large number of inputs where we have A, B, C, D, E with R, and all that, MCDC requires considerably more test cases than any of the coverage measures discussed above. We'll take some examples. Here you can see a logical AND gate. Where A, B, C inputs are being ANDed in this block, and the result of this is placed in D. So it is called a 3-input AND gate. That means there are 3 inputs A, B, C. There is an AND gate here. You can see A, B, C is an AND gate, and D is the result. So this is how they represent the different gates. So that gate representation are all part of the engineering curriculum, where we have OR and all the stuff represented this way. These are all typically used in the requirements, and against those requirements test cases will be written. So okay, so in this table, whatever the number of minimum tests for these 3 input AND gates are listed. How are they listed? Let us see. Okay, test case numbers, there are about 1, 2, 3, 4 test cases are there. Sorry, 3 test case numbers have been specified. Each of them considering 1 at a time. That means A as an input, B as an input, C as an input. Also, we need to have a D as an output as the 4th condition. So those many test cases need to be exercised. So what are the tests that can have for this MCDC? First one, A, B, C are provided as T. That is true. The output will be true. Similarly, A, B, C is provided as input as false and B as true, to the output is same. Sorry, output is false. Similarly, third one, we modify B as a false and A as true, output D becomes false. And in the fourth case, the input C is provided with the input as F and the output is F. So basically the output is depending on the false conditions that can be driven either through this. So is it because of C only the false has come? How we are going to exercise? By providing the input C, F. Suppose if the D is providing false in any case, how are you going to test for A and B? So in that case, C we need to test it as true, and in the next test sequence we are going to put A as true and B as false. Likewise, we are going to have a table. This table is called truth table. That is why the MCDC approach is used for such expressions where we use AND gate, OR gate, and all. So these many tests we are going to have. One test will take 1, 2, 3, 4 values. Sorry, the columns. The first one takes all the consideration as true. Second one, all the considerations as different values. The output is same in 2, 3, 4, whereas the output could be derived due to independency in either A, B, C, etc. So that is how MCDC truth table is drawn and the test cases are done. Let's take another example. Here we will go through a 3-input OR gate where A, B, C are fed into an OR gate and the result of the OR gate is D. In the previous example, we have D gate as D as an output derived from the AND gate. So what are the test cases that we can draw? So we need to consider input A, input B, input C. In order to achieve output D, what are the conditions that we need to exercise? So this is a table which talks about minimum tests that we need to have. Okay. In the first test case, we are going to have input A, B, C all are as false. The output will be false. In the rest of the test cases, you can see 2, 3, 4. The output is always true. Why? Because one of the input is true, right? So why it is called as a minimum, we need to understand. We may have one more, say suppose fifth, let us see. What is the other combination we can have? Do we have true, true, false? Sixth. Do we have false, true, true? Yes. Okay. So basically, which is the deciding factor here? Not the false, right? The output is derived purely based on the output true is purely based on the fact that any of the input is true. So we need to drive any of the input. In the first case, any can become A, the second case B, third case is C. So other cases like both cases A and B true doesn't matter because already we have seen the output as true. So this is the minimum number of tests. Of course, depending on the expression condition, we can have more, but it is like a tedious relevant selection. But as part of the MCDC is concerned, the independency need to be shown. How we want to show independencies for each of the input that is responsible or effective in terms of the output have to be driven. Similarly, we have seen any of the input in terms of false will result in the false as output. So it doesn't matter 2 are false or all 3 are false. Always the result is false. The independency will be shown with the help of each of the inputs. So likewise, we can have for XOR not comparators as inputs that is used in the logical expressions. Maybe you can take an exercise for XOR and not. So not is very simple. You know that not of A equals B. Similarly, A XOR B. You know the truth table how to draw because logical expression we know. So you can write what are the minimum tests that are needed to test this expression. The first one and the second one. So this is an exercise or today's session will take. Okay. So that is about MCDC. The most important method that is used in the DO infinite B life cycle process. Okay. So that is about MCDC. I think we will continue the other aspects of testing in the next session. We will go through some of the words that we have added. Maybe what we can add today is MCDC. Okay. DO infinite B machine coverage and all are part of the study only. Anything we have missed? CSAJ, then we have test design, inputs, outputs, and all, branch condition testing, branch condition combination testing, Boolean operands. You can add. Okay. So what we do is we'll add some more words today, which we have studied. The MCDC is not listed. Boolean expression, logic. Okay, so rest of the words like branch, condition, decision, data flow, timing analysis, analyzers. I think timing analysis, analyzers, perform analysis, working on test. We will study in the future classes. MCDC we have seen. Boolean expression, logic we have gone through. And some of the recent sessions we had was on LOC statements, coverage, model-based testing, instrumentation, etc. I will not go through everything, but to have an understanding about embedded software testing, we need to be aware of the knowledgeable of this type of testing. Okay, so let us study about few of the glossary. Is referred from testing standards book. Physical test case, detailed description of a test situation or logical test case containing the initial situation, actions to be taken, and the expected results explicitly defined in concrete values. The level of detail is such that when the test is executed at a later stage, it is done as efficiently as possible. It means we will have the concrete steps in terms of values and all that. So physically we lay it out in a descriptive manner. So that is nothing but physical test case. Plant, the environment. Plant normally they are not used, but some of the production industry they use testing plant, test plant, etc. The environment that interacts with an embedded system. Precondition is a very important term. So it's an environmental and state condition which must be fulfilled before the component can be executed with a particular input value. That means without the preconditions, the tests following that precondition cannot be executed. The preconditions have to be there in place. Rapid prototyping is a development test level. Okay, the test level where a simulated embedded system is tested while connected to a real environment. It means rapid prototyping testing is a test level. The system, embedded system is simulated, is tested, which is connected to the real environment. It could be on a host. Real-time system where correctness of the system behavior depends on the exact moment when the output is produced. That means where the time is very hard. It's also called as hard real-time system. Real-time systems basically deals with the behavior where the different events that are going to happen within the embedded system should be happening at the right time, exact moment. For example, real-time embedded systems, we have X-ray machines where a user presses one button, so it should respond within certain time or at that moment. So that sort of systems we have a real-time embedded system implemented. Regression testing is a very important term as well. Retesting of a previously tested test object following modification to ensure that faults have not been introduced or uncovered as a result of the changes made. That means we have found some issues in our first or primary testing, and that has been fixed either in the requirements or design or in the implementation. And the same tests without modifying any test suite or test environment or the test cases, we are going to test that piece of the fixed code and results we are going to achieve in terms of test being passed. Result, we know that actual result or expected result. The actual result is what we get it on the system when it is subjected to a specific test. The expected result is what being expected, which is put as part of the test case design. Risk is a chance of failure into damage. That means while doing the testing of the embedded systems, it could, based on the inputs or the robustness or the load that we have on the system, it could impact the efficiency or the behavior of the embedded system, and it could result in a damage. So risk is considered as a chance of failure multiplied by damage. Risk reporting, description of the extent to which the system meets the specified quality requirements and the risks associated with bringing a particular version into production, including any way available alternatives. That means we have mitigation, how we can de-risk those aspects. All will be part of the risk reporting. So with that, we will end this today's session, and we will take up the white boxes, some of the pending testing in the next session.